Look up tonight. Every star you see gives you the same lie. They look close together, like cities on a map. Some of them even have planets, whole solar systems with worlds that could hold oceans, atmospheres, maybe life. And the nearest one, the Alpha Centauri system, sits just 4 light years away. That sounds almost reachable, almost neighbourly. But here is what nobody tells you. The emptiness between your solar system and that one is so vast, so brutally enormous, that it breaks every comfortable idea you have ever had about the local universe. The distance is not just far, it is a kind of far that erases the meaning of the word neighbour. And once you understand what actually fills that gap, you will never look at the night sky the same way again. If you enjoy having your sense of scale permanently shattered, hit that like button and subscribe. It helps this channel keep going more than you know, and I genuinely appreciate every one of you who sticks around for these deep journeys into the cosmos. Now, get yourself comfortable. Let's begin. Go outside tonight. Find a dark place, somewhere away from the streetlights and the glow of the city, and look up. If the sky is clear, you will see stars, thousands of them. They will fill your field of vision from one horizon to the other, bright points scattered across the darkness in every direction, some clustered together, others drifting in isolation, a few brilliant enough to catch your attention immediately. The sky will look full, it will look rich, it will look like a neighborhood, and that is the lie. Your eyes are doing something your brain cannot correct for. They are collecting photons from stars that sit at wildly different distances, some dozens of light years away, others hundreds, a few thousands, and they are compressing all of that staggering three-dimensional depth into a single flat dome overhead. The sky you see is not a map. It is a projection. Every star appears to sit on the same curved surface, as though they were all pinned to the inside of a dark sphere just out of reach. The bright ones look close, the faint ones look far, but brightness has almost nothing to do with distance. A dim red dwarf 4 light years away can be invisible to the naked eye, while a blue supergiant 2,000 light years away blazes like a beacon. Your eyes cannot tell the difference. Your brain fills in the gap with an assumption that feels natural and is completely wrong. It assumes the stars are relatively near each other. It assumes the sky is a kind of map you could navigate. It assumes that the phrase neighbouring star system means something similar to what the word neighbour means on Earth. It does not. And the distance hiding behind that word is so extreme that once you see it clearly, it changes the meaning of everything the night sky pretends to show you. Start with the closest one. It is not a single star, it is a triple system. 3 stars bound together by gravity. The 2 main components, Alpha Centauri A and Alpha Centauri B, orbit each other roughly every 80 years at distances comparable to the spacing between our Sun and the outer planets. The third member, Proxima Centauri, is a small red dwarf that drifts much farther out, currently sitting about 0.21 light years from the central pair, circling them on an immense orbit that takes over 500,000 years to complete. Proxima Centauri holds the title of the nearest individual star to our Sun, at a distance of approximately 4.24 light years. The central pair sits slightly farther, at about 4.37 light years. 4.37 light years. Say it out loud and it sounds manageable. It even sounds close. Astronomers call it the nearest star system, and that language reinforces the feeling, nearest, as though it is just around the corner. As though the gap between our solar system and the Alpha Centauri system is a short commute by cosmic standards. Every popular science article about exoplanets mentions this distance casually, as if it were a known and roughly comfortable quantity. 4 light years. Not far at all. Practically next door, but here is what the number actually means. 1 light year is the distance that light travels in a single year. Light moves at approximately 186,000 miles per second. Not per hour, per second. In 1 second, a beam of light crosses a distance roughly equivalent to circling the Earth 7.5 times. In 1 minute, it reaches beyond the orbit of Mercury. In about 8 minutes, it travels from the Sun to the Earth. In roughly 5.5 hours, it passes Pluto. That is light speed. the fastest anything in the universe can move according to confirmed physics. And it takes that beam, moving at that incomprehensible velocity, 1 full year to travel a single light year. 1 light year equals approximately 5.88 trillion miles. Now multiply that by 4.37. The distance from our solar system to the Alpha Centauri system spans roughly 25.7 trillion miles. 25 followed by 12 zeros and then some. This is not a number the human brain can feel. You can write it down, you can say it, but you cannot experience it. Your mind has no framework for processing a quantity this large because nothing in the environment where human cognition evolved required it. Our ancestors needed to judge distances across savannas, across rivers, across valleys. The farthest thing any early human ever needed to estimate was the horizon, a few miles away. 25 trillion miles is not an extension of that skill. It is a different category entirely. It is a distance so large that the words used to describe it become decorative. They stop conveying information and start functioning as placeholders for something the brain quietly refuses to compute. And that refusal is exactly where the lie takes hold. When you hear 4.37 light years and feel a mild sense of distance, your brain is doing what it always does with large numbers. It is compressing, it is rounding, it is filing the number under far but finite and moving on. The same mental process that lets you casually accept that the sun is 93 million miles away or that the Milky Way contains 400 billion stars is the process that makes 4 light years sound like a road trip. Your brain treats cosmic distances the way it treats large financial figures. It registers the category big without truly grasping the magnitude. $1 million and $1 billion both live in the mental folder labeled a lot of money, even though 1 billion is 1,000 times larger. 4 light years and 400 light years both live in the folder labeled far away in space, even though one is 100 times the other. This compression is not laziness. It is a survival mechanism. The human brain is not designed to operate at cosmic scales. It is designed to keep you alive in an environment measured in footsteps, arm lengths, and throwing distances. When it encounters a number like 25 trillion miles, it does the only thing it can. It shrinks the number into something emotionally manageable and moves on. That shrinking is what makes the night sky feel like a neighborhood. And it is what makes the distance between solar systems feel like a problem rather than a wall. To feel the distance, instead of just knowing it, you need a different kind of translation. Forget the raw numbers for a moment. Think about something you already understand. Think about space travel as humans have actually done it. The farthest any human-made object has ever traveled from Earth is Voyager 1. Launched in 1977, Voyager 1 flew past Jupiter and Saturn, completed its planetary mission, and then kept going. It has been traveling away from Earth ever since, moving at approximately 38,000 miles per hour. That is fast by any human standard. It is roughly 50 times the speed of a bullet. Voyager 1 crosses nearly 1 million miles every single day. By November of 2026, Voyager 1 will reach a historic milestone. It will be 1 light day from Earth, approximately 16 billion miles away. At that point, a radio signal sent from NASA's Deep Space Network will take a full 24 hours to reach the spacecraft. A command sent in the morning will not arrive until the following morning. A response will not return until the day after that. 2 full days for a single exchange of information, at the speed of light, with an object that has been flying away from Earth for nearly 50 years. 1 light day. That is what 50 years of continuous travel at 38,000 miles per hour gets you. 1 light day. The Alpha Centauri system is over 1,500 light days away. Sit with that for a moment. Voyager 1, the fastest and farthest object humanity has ever sent into the void, has spent half a century reaching a distance that represents roughly 1/1600th of the journey to the nearest star system. If Voyager 1 were aimed at Alpha Centauri, which it is not, it would arrive in approximately 75,000 years. 75,000 years. That is longer than modern humans have existed as a species. It is longer than every civilization, every empire, every written language, every technological revolution in human history combined. The entire arc of everything humanity has ever accomplished fits inside the travel time to the nearest star system at the fastest speed we have ever achieved. And that system is the close one. That is the neighbour. This is where people usually nod and say, yes, space is big, I knew that. But recognizing that the number is large is not the same as understanding what it does. The distance between solar systems does not simply make travel slow. It imposes a kind of separation that has no equivalent in human experience. Consider what a distance of 25 trillion miles actually contains. The answer is almost nothing. Between our solar system and the Alpha Centauri system, there is no fuel station, no landmark, no rest stop, no gravity well to catch you if something goes wrong. There is interstellar medium, a scattering of hydrogen atoms so sparse that a cubic centimetre of this space contains roughly one atom. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimetre. The space between star systems is not just empty, it is empty on a level that the word empty cannot adequately describe. It is a vacuum so thorough that it makes the best laboratory vacuums on Earth look like a crowded room. This vacuum extends in every direction for trillions of miles. No structure, no shelter, no boundary marker. If you launched a probe and its engine failed halfway through the crossing, the probe would drift through that void forever. Nothing would stop it. Nothing would catch it. Nothing would even notice it. The space between solar systems is not a gap between two places. It is an absence so vast that the places on either end become almost theoretical to each other. Now imagine, just for a moment, that you could stand in the middle of that absence. Not in a ship, not in a suit, just your consciousness, suspended at the halfway point between our Sun and Alpha Centauri, roughly 2.2 light-years from each. What would you see? You would see stars, the same stars you see from Earth, arranged in nearly the same constellations, because 2 light-years of displacement is not enough to visibly shift patterns drawn by stars that sit hundreds or thousands of light-years away. The sky would look almost identical to the sky you know, but the Sun would no longer dominate it. From this midpoint, our Sun would appear as one of the brighter stars in the sky, conspicuous in luminosity but identical in kind to every other point of light overhead, just a dot with nothing to reveal that an entire planetary system orbited around it. Alpha Centauri would appear similarly bright in the opposite direction, equally featureless, equally silent about the worlds it might contain. You would have no visible cue telling you that 2 entire solar systems, 2 complete gravitational territories containing planets and moons and comets, and billions of miles of structure existed on either side of you. No dust cloud would glow faintly in their direction. No band of light would indicate where matter thickened into something meaningful. You would float in perfect blackness, interrupted only by the ancient, static, evenly distributed pinpoints of starlight that look the same from almost anywhere in the galaxy. The void would offer you no sign that you were between anything at all. It would look exactly like being nowhere. And here is the part that changes everything. Stars are not destinations. When you look at Alpha Centauri in the night sky, you see a point of light. Your brain registers it as a thing, a single object, a place you could in principle go to. But Alpha Centauri is not a point, it is a system. It is 3 stars with their own gravitational territories, their own potential planets, their own zones of influence extending outward for billions of miles. Our Sun is the same. It is not a dot on a map. It is the centre of an enormous gravitational domain that stretches outward past the planets, past the Kuiper belt, past the scattered disk, all the way out to the Oort Cloud, a shell of icy bodies that may extend 50,000 to 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. 100,000 astronomical units is roughly 1.6 light-years. That means our own solar system, measured to its theoretical outer boundary, has a diameter of approximately 3.2 light-years. The Sun's gravitational influence reaches more than a light-year and a half in every direction. The Alpha Centauri system, being a more massive multi-star system, likely has a comparable or even larger zone of influence. These are not small objects separated by large gaps. These are enormous territories, whole gravitational nations, separated by a void that is large even compared to their own immense sizes. The distance between solar systems is not the distance between two dots. It is the distance between two empires, and the void between those empires is not just a number to be quoted in a documentary. It is the defining feature of our local cosmic environment. The stars are not what fill the space around us. The emptiness is what fills the space around us. The stars are rare, isolated exceptions. Think about what this means for the night sky. Every star you see tonight is the center of its own vast gravitational domain. Every one of those domains is separated from every other domain by trillions of miles of functionally empty space. The sky looks full. The reality is sparse. If you could see the true three-dimensional distribution of nearby star systems, you would not see a neighborhood. You would see a scattering of distant campfires in an endless dark desert, each fire burning alone, each one separated from the next by a walk so long that no one who started it would live to finish it. And this is only the nearest system, the nearest one, the closest campfire. Step past Alpha Centauri and the distances get worse immediately. Barnard's star sits at approximately 5.96 light-years. That is roughly 35 trillion miles. Wolf 359 is at approximately 7.9 light-years, about 46 trillion miles. Lalande 21185 is at approximately 8.3 light-years. Sirius, the brightest star in the night sky, the one that looks so close and so bold, sits at roughly 8.6 light-years, more than 50 trillion miles away. Each step outward from our solar system increases the emptiness, widens the void, and deepens the isolation. Within 10 light-years of our Sun, there are only about a dozen known star systems. A dozen. In a sphere of space 10 light-years in radius, a volume encompassing over 4,000 cubic light-years, you will find roughly 12 to 15 stellar neighbors. That is not a community. That is a scattering so thin that each system sits in its own private ocean of vacuum. If you placed a marble at the center of a football field to represent our Sun, and you scaled everything proportionally, the nearest star system would be another marble, sitting on a completely different football field in a completely different city. And between those two fields, between those two marbles, there would be nothing. No other marbles, no structures, no landmarks, just empty ground, stretching in every direction farther than you could see. Now here is what makes this worse than a simple large number. It is not just that the distances are big. It is that the distances are invisible. You cannot see the void between star systems. You can only see the stars. The night sky is a display of luminous objects that hides the dominant reality between them. It is as if you looked out over a dark ocean and saw only the scattered lights of distant ships. You would assume the ocean was navigable. You would assume the ships were reachable. You would have no way of knowing that the water between them was thousands of miles of open sea, freezing cold, with no land in sight and no way to call for help. The lights would give you false confidence. The darkness would hide the danger. That is what the night sky does. It shows you the campfires and hides the desert. It shows you the ships and hides the ocean. It shows you stars that look like neighbors and hides the void that makes them strangers. This illusion is so powerful that it shapes the way entire civilizations think about space. We build stories about interstellar travel. We imagine warp drives, hyperspace, jump gates, and faster-than-light communication. We invent entire fictional universes where star systems are connected like cities on a highway. We do this because the sky tells us it should be possible. The sky shows us a cosmos that looks populated, that looks structured, that looks almost navigable. The sky tells us we are surrounded by potential destinations. It never tells us that between every pair of those destinations lies a gulf so large that crossing it would outlast everything we have ever built. The ancient Greeks thought the stars were holes in a dark sphere, tiny punctures letting the light of a cosmic fire shine through. They were wrong about the mechanism, but right about one thing. The stars do look close together. They look as though they share a surface, as though they inhabit the same thin shell of sky, as though the distances between them are small enough to ignore. That instinct, the instinct to see the sky as a surface rather than a depth, is the root of the lie. It is the reason people hear, 4.37 light years, and feel a manageable distance. It is the reason the phrase nearest star system sounds almost inviting. It is the reason the void between solar systems stays invisible even though it is the single most dominant feature of our local universe. And that void is not just a distance to be quoted, it is a barrier with consequences. Consider what it means that Voyager 1 will reach 1 light day from Earth in late 2026, and it will have taken nearly 50 years to get there. Consider that the nearest star system is more than 1,500 times farther than that single light day. Consider that between here and there, for every mile of that crossing, there is almost nothing. No fuel, no gravity, no signal relay, no rescue, just vacuum, cold, and time stretching out in quantities that make human lifespans look like a camera flash in a dark room. The night sky hides all of this. It shows you the lights and lets you imagine the rest. But the rest is what matters. The rest is what defines whether those lights are neighbours or strangers. The rest is what determines whether the local universe is a community or a prison. And the rest, the invisible rest, is far worse than most people ever realise. But to understand how bad it truly is, you first need to understand something most people get wrong. The distance between solar systems is not measured from star to star. It is measured from the edge of one entire gravitational territory to the edge of another. And those territories are far larger than almost anyone imagines. That changes the picture in ways that make the void even harder to accept. Most people, when they think about a solar system, picture the planets. They see the familiar diagram from school, a bright sun at the centre, a neat sequence of orbiting spheres radiating outward, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all arranged in concentric lanes like a cosmic racetrack. Maybe they remember the asteroid belt between Mars and Jupiter. Maybe they recall that Pluto was reclassified. The mental image is tidy, contained, and fundamentally misleading, because when that diagram ends, when the last planet fades and the textbook labels stop, the solar system does not end. It keeps going. And it keeps going so far beyond the last planet that the planets themselves become an almost irrelevant footnote in the full story of what a solar system actually is. Neptune, the outermost major planet, orbits the Sun at an average distance of approximately 30 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. So Neptune sits about 2.8 billion miles from the Sun. That sounds enormous, and it is enormous by any standard humans can physically experience. Light itself takes over 4 hours to travel from the Sun to Neptune. A spacecraft travelling at Voyager 1's speed would need over 12 years to cover the same distance. The planetary zone of our solar system, from Mercury's tight inner orbit all the way out to Neptune's frigid path, spans a diameter of roughly 60 astronomical units. That is the part you see in the diagrams. That is the part most people think of when they hear the words solar system. It represents less than 0.1% of the actual territory. Beyond Neptune lies the Kuiper Belt, a donut-shaped region of icy bodies that stretches from roughly 30 to about 50 astronomical units from the Sun. Pluto lives here. So do thousands of other frozen objects, remnants from the formation of the solar system that never coalesced into a full planet. The Kuiper Belt is vast by planetary standards, extending billions of miles beyond Neptune, and it was only confirmed observationally in the early 1990s. For most of human history, we did not even know it existed. But the Kuiper Belt is still close to home compared to what lies beyond it. Past the Kuiper Belt, the solar system continues through a region called the scattered disk, home to objects on wild, elongated orbits that can carry them hundreds of astronomical units from the Sun before swinging back inward. Sedna, one of the most distant known objects in our solar system, travels on an orbit that takes it from about 76 astronomical units at its closest approach to the Sun out to nearly 900 astronomical units at its farthest. Its orbital period is approximately 11,000 years. Sedna was discovered in 2003 and has not completed even a fraction of one orbit since humans first looked at the sky. It drifts through a region of space so remote that the Sun, from Sedna's farthest point, would appear as nothing more than an unusually bright star. and even Sedna is nowhere near the edge. The true outer boundary of our solar system is defined not by planets, not by the Kuiper belt, not by the scattered disk, but by the Oort Cloud. This is a theoretical shell of icy bodies believed to surround the Sun in a vast, roughly spherical halo. No telescope has ever directly observed the Oort Cloud. Its existence is inferred from the behavior of long-period comets, objects that plunge into the inner solar system on orbits so elongated that they must originate from immense distances. The mathematics of their trajectories points consistently to a source region beginning somewhere around 1,000 astronomical units from the Sun and extending outward to perhaps 50,000 or even 100,000 astronomical units. 100,000 astronomical units. Let that number register. Neptune, the outermost planet, sits at 30 astronomical units. The outer edge of the Oort Cloud may sit at 100,000. That is more than 3,300 times farther from the Sun than Neptune. If you drew a line from the Sun to Neptune and called it 1 inch, the line from the Sun to the outer Oort Cloud would stretch over 275 feet. The planets, all 8 of them, every world you have ever seen in a photograph or read about in a textbook, occupy the first inch of a solar system that extends the length of a football field and beyond the end zone. At 100,000 astronomical units, the outer Oort Cloud sits approximately 1.6 light-years from the Sun, in every direction. That gives our solar system a theoretical diameter of roughly 3.2 light-years, measured from one side of the Oort Cloud through the Sun to the other side. 3.2 light-years across. The planetary zone, the part with the worlds and the moons and the rings and everything we have ever visited with a spacecraft, spans a diameter of roughly 60 astronomical units, or about 0.001 light-years. The full solar system is more than 3,000 times wider than the part that contains the planets. This is what people miss when they talk about the distance between solar systems. They imagine the journey from one star to another as a trip between 2 points, as though each system were a dot on a map. But each system is not a dot, it is a territory. It is a gravitational domain so vast that simply crossing your own system from one edge of the Oort Cloud to the other would take tens of thousands of years at any speed humanity has achieved. The solar system is not a small island in a big ocean. It is a continent-sized structure, and the space between continents is measured in light-years even after you account for how enormous each continent already is. Now apply this understanding to the distance between our solar system and the Alpha Centauri system. The center-to-center distance, Sun to Alpha Centauri A, is approximately 4.37 light-years, or about 276,000 astronomical units. Our Oort Cloud may extend roughly 50,000 astronomical units outward from the Sun, which is about 0.8 light-years. If the Alpha Centauri system, with its 3 stars and their combined gravitational influence, has a comparable outer boundary, then the outer edges of the 2 systems may be separated by a gap of only 2 to 3 light-years. On paper, this sounds like the systems almost touch. Their gravitational territories may even overlap in the regions where stellar influence fades and the gravity of the galaxy itself becomes the dominant force. But do not let that smaller number comfort you. 2 to 3 light-years of true interstellar vacuum, the gap between the outermost frozen objects of one system and the outermost frozen objects of another, still represents 12 to 18 trillion miles of space, containing effectively nothing. And reaching the edge of our own system in the first place requires a journey that dwarfs anything humanity has attempted. Voyager 1, the farthest human-made object, currently sits at approximately 170 astronomical units from the Sun. The inner edge of the Oort Cloud may begin around 1,000 astronomical units. Voyager 1 has not yet reached the front porch of our own solar system's true boundary, and it's been travelling for nearly 50 years. At its current speed, it will not enter the Oort Cloud for another 300 years. It will not exit the far side for approximately 30,000 years. 30,000 years to cross your own solar system. And then, the real emptiness begins. This is the first reason the invisible distance between solar systems is worse than people think. It is not simply that the star-to-star measurement is large. It is that the star-to-star measurement hides the true scope of the journey. Before you ever enter the void between systems, you must first escape your own, And your own system is so enormous that escaping it is itself a multi-millennial undertaking. The journey from Earth to the Alpha Centauri system is not a journey from one dot to another dot 4.37 light-years away. It is a journey from deep inside, one vast gravitational territory, across the remaining expanse of that territory, through a gulf of interstellar vacuum, and then into the equally vast territory of the neighbouring system. Every stage of that journey is immense. Every stage is dominated by emptiness, and the total distance, measured from inhabited world to potentially habitable world, rather than from star to star, could be functionally indistinguishable from the raw light-year figure, because the planets in both systems sit so deep inside their respective territories that the Oort Cloud crossing on either end adds enormous additional distance to any practical mission. But the Alpha Centauri system is singular in its proximity. It is the one exception, the one freak of local geometry that places another star system within spitting distance by cosmic standards. Step past it, and the isolation escalates immediately. Barnard's star, the next nearest system after Alpha Centauri, sits at approximately 5.96 light-years from the Sun. That is roughly 37% farther than Alpha Centauri. In absolute terms, the gap between the two distances sounds modest, about 1.6 light-years, but 1.6 light-years is approximately 9.4 trillion additional miles of vacuum. Barnard's star is a solitary red dwarf, faint and small, invisible to the naked eye despite being the second closest star system to our own. It was only discovered in 1916 by astronomer Edward Emerson Barnard, who noticed its unusually rapid motion across the sky. For centuries before that, humanity had no idea it was there. Planets have been confirmed around Barnard's star as recently as 2024 and 2025, with at least 4 small worlds now identified, all of them too close to the star to sit in the habitable zone. A complete planetary system confirmed to exist, sitting 6 light-years away, and we knew nothing about its worlds until last year. After Barnard's star, the next known objects are the brown dwarf binary Lumen 16 at approximately 6.5 light-years, discovered only in 2013, then a sub-brown dwarf at roughly 7.5 light-years, then Wolf 359 at approximately 7.9 light-years, then Larland 21-1-85 at about 8.3 light-years, then Sirius at approximately 8.6 light-years. Each system sits farther out. Each gap widens. The distances are not closing, they are opening. Within 10 light-years of the Sun, the total count of known star systems is roughly 12 to 15. Within 20 light-years, the count rises to approximately 100 known stars in perhaps 70 or 80 distinct systems, since many are binaries or triples. That sounds like more, but consider the volume of space involved. A sphere with a radius of 20 light-years contains over 33,000 cubic light-years of space. 100 stars scattered across 33,000 cubic light-years means that on average, there is 1 star for every 330 cubic light-years. Each star system occupies its own private pocket of vacuum, so large that you could fit entire civilizations inside the gap between any two of them and still have room left over that no one would ever visit. And here is something most people never consider. Those 100 stars are not arranged on a flat surface. The night sky makes it look that way. You see stars scattered across a 2-dimensional dome, and your brain unconsciously assumes they sit in a relatively thin layer, like towns sprinkled across a flat plain. But the local stellar volume is not flat. It is a sphere. Those systems are scattered in 3 dimensions, above and below the galactic plane as well as across it. Some of the nearest stars sit tens of light-years above our position relative to the galactic disk. Others sit far below. The separation between systems is not just horizontal, it is vertical, diagonal, angular. 2 systems that appear close together in the night sky, projected onto the same patch of darkness, may actually be separated by enormous distances in depth. One sitting 5 light-years away and the other sitting 15, with 10 light-years of empty space between them that your eyes compress into the illusion that they are neighbours. This 3-dimensional scattering is what makes the local stellar environment so profoundly sparse. If the 100 nearest stars were arranged in a flat grid, like streetlights on a plane, the spacing would already be enormous. But they are not arranged in a grid. They are scattered through a volume, which means the distances between them grow in every direction simultaneously. A star that sits 6 light-years to your left and 4 light-years above the galactic plane is not 6 light-years away. The actual distance, measured through 3-dimensional space, is longer. The diagonal is always longer than either side. This is basic geometry, but applied at cosmic scales, it means the true separations between systems are often larger than the simple catalogue distances suggest when people read them as though the stars sat on a flat map. Picture yourself standing in the centre of a vast, dark, 3-dimensional space. You hold a dim flashlight. Scattered around you, in every direction, above, below, left, right, in front, behind, are other tiny flashlights, each one held by someone standing alone in the dark. The nearest one is 4 light-years away. The next is 6 light-years away, but in a completely different direction. The one after that is 8 light-years away and sits far above your head. You can see their lights, they can see yours, but the 3-dimensional distances between each pair of lights are so vast and so varied in direction that no two of them share a common path. There is no line you could walk that would take you past more than one. Every journey is a solo crossing to a single destination, through a unique corridor of emptiness that no other traveller would ever use. There are no highways in 3-dimensional scattering. There are only isolated, unrepeatable paths through a void that extends equally in every direction. This 3-dimensional reality is invisible from the ground. The night sky collapses all of that depth into a flat picture. Stars that are separated by vast chasms in depth appear to sit side by side in the same constellation. The human brain, which evolved to navigate a 2-dimensional surface and judge distances on a flat horizon, has no mechanism for perceiving depth at interstellar scales. We cannot tell, by looking, whether a star is 4 light-years away or 40. We cannot sense whether 2 stars that appear close together on the sky are actually close in space or separated by a gulf so large that travelling from one to the other would take longer than travelling from either one to us. The flat projection of the night sky is not merely simplified, it is deceptive. It erases the vertical dimension entirely and compresses the horizontal dimensions beyond recognition. What remains is a picture that looks organised, structured, and navigable. The 3-dimensional truth is none of those things. Within just the nearest 20 light-years, systems are scattered at angles and depths that make every pair isolated from every other pair. Ross, 248, sits roughly 10.3 light-years away in one direction. 61 Cygni sits about 11.4 light-years away in a completely different direction. Epsilon Indi sits 11.8 light-years away in yet another direction. Procyon sits 11.5 light-years away in still another. None of these systems are close to each other. They are all roughly equidistant from the Sun, but spread across different sectors of a vast sphere, like lonely outposts stationed at maximum distance from one another around a dark perimeter. The local stellar volume does not look like a cluster from inside. It looks like a sparse, random scattering of points positioned as though someone had thrown a handful of sand into a gymnasium, and each grain had landed as far from its nearest companion as chance allowed. This is not a neighbourhood. It is a darkness with rare, scattered points of warmth, each one so distant from the next that reaching any of them from any other would consume more time than every civilization in human history combined. The sparseness of the local stellar environment is not an accident. It reflects the actual density of stars in our region of the Milky Way. The Sun sits in the Orion Arm, a relatively minor spiral arm in the outer regions of the galaxy. Star density here is moderate by galactic standards. Near the galactic centre, stars are packed much more tightly, with average separations measured in fractions of a light-year. In the sparse outer halo, separations can stretch to dozens of light-years. Our neighbourhood falls somewhere in the middle, with typical nearest neighbour distances of 4 to 6 light-years. That means the Alpha Centauri system is not unusually close. It is typical. The gulf between our system and the next is what the galaxy considers normal spacing for this region. There is no crowded cluster of nearby systems hidden just out of view. There is no dense pocket of stars waiting to be discovered a few light-years farther. The local environment is what it is, a scattering of isolated gravitational territories separated by trillions of miles of vacuum, extending in every direction, with no sign of clustering and no prospect of improvement. And now consider what recent discoveries are revealing about these isolated neighbours. In 2025, the James Webb Space Telescope detected a candidate planet around Alpha Centauri A. If confirmed, it would be a roughly Saturn-sized world orbiting the nearest Sun-like star. This is not just a detection of light from a distant point. It is a glimpse of a potentially complete planetary system across the void. Alpha Centauri A may have gas giants. Proxima Centauri is already confirmed to host at least 2 planets, including Proxima b, an Earth-sized world sitting in the habitable zone where liquid water could theoretically exist on its surface. Barnard's star has at least 4 confirmed planets. These are not barren stars glowing uselessly across the emptiness. These are entire worlds, whole collections of planets and moons orbiting in their own gravitational territories, sitting across gulfs so large that we only just developed the technology to confirm their existence. This is the profound strangeness of the local universe. The systems are real, the planets are real, the possibility of oceans, atmospheres, and even biology on those worlds is scientifically plausible. And the distances separating them from us are so extreme that knowing they exist and being able to reach them are 2 entirely different categories of achievement, separated by engineering challenges that may not be solvable within any foreseeable time frame. Think about what it means to know that an Earth-sized planet orbits in the habitable zone of the nearest star, 4.24 light-years away, and to simultaneously know that no spacecraft we have ever built could reach it in less than tens of thousands of years. The knowledge and the distance exist in the same reality, and they create a tension that has no resolution. You can see the destination. You can study the destination. You can even imagine standing on the destination, but you cannot go there. Not with current technology. Not with any technology that has been seriously demonstrated. The island exists. The ocean between you and the island is real, and the ocean is so wide that the island might as well be imaginary for all the good knowing about it does. This is the second reason the invisible distance between solar systems is worse than people think. It is not merely that the gap is large, it is that the gap separates complete worlds from each other. These are not empty stars divided by empty space. These are full systems, planetary architectures, potential biospheres, divided by emptiness so vast that the systems might as well exist in separate universes. The stars are not lonely. Each star has its own family of worlds. The loneliness is between the families. And the space that creates that loneliness is invisible to anyone standing on any planet, in any system, because you cannot see the void. You can only see the stars on the other side of it, glowing with the false promise that they are close enough to matter. The Oort Cloud makes this worse in a way that is rarely discussed. Because our solar system extends roughly 1.6 light-years in every direction, and because the Alpha Centauri system has its own extended zone of influence, the 2 systems are not separated by 4.37 light-years of pure open vacuum. They are separated by 4.37 light-years that include the deep outer reaches of both systems. Some of that space contains material, sparse, frozen, drifting debris from the Oort clouds of both stars. In theory, there may be regions where the gravitational influences overlap, where icy bodies are tugged by the Sun and by Proxima Centauri in roughly equal measure. This overlap zone, if it exists, would represent the closest thing to a border between the 2 systems. But this border is not a bridge. It is a fog bank. The Oort cloud is not a dense shell you can land on or push off from. It is an immensely diffuse scattering of objects, each one separated from its nearest neighbour by millions of miles. The total mass of the Oort cloud is estimated at roughly a few Earth masses, but that mass is distributed across a volume so staggeringly large that the density is effectively 0 by any human standard. Travelling through the Oort cloud would feel identical to travelling through open interstellar space. You would see nothing. You would encounter nothing. The boundary of the solar system is not a wall or a fence or even a line in the sand. It is a gradual fading of gravitational influence that happens across distances measured in light years. The edge of your solar system is not a place. It is a process that takes light years to complete. And that process, that slow fade from one gravitational domain to the next, is what fills the void between solar systems. It is not clean emptiness with sharp borders. It is a gradual, silent, lightless transition from one system's outermost influence to another system's outermost influence, stretched across trillions of miles of space where nothing significant exists, where no structure provides shelter, where no object offers a foothold, and where the only evidence that you are closer to one system than another is a calculation based on gravitational math that no human sense could ever detect. The void between solar systems is not a gap between two places. It is the slow dissolve of one place into nothing, followed by trillions of miles of that nothing, followed by the equally slow emergence of another place from the same nothing. The islands are real. The worlds on those islands are real, and the ocean between them is not just wide. It is made of a substance that is the closest thing in nature to absolute non-existence. Every diagram you have ever seen of the solar system lied to you by omission. It showed you the planets and stopped. It let you believe the solar system was a compact, tidy structure surrounded by open space. The truth is that the planets are a tiny bright core buried deep inside a gravitational territory that extends for light years in every direction. And the neighbouring systems, the ones that look so close in the night sky, are equally vast territories separated by a void that dwarfs even their enormous sizes. The night sky hid the void by showing you only the stars. Now you know the stars are not points, they are empires, and the empires are separated by an emptiness that is not merely large, but functionally absolute. But knowing the size of the islands and the width of the ocean is only part of the story. The real shock comes when you try to do something with that knowledge, when you try to cross the void, when you try to send a message across it, when you try to imagine what it would mean to live on one island and need help from another. The distances do not merely separate, they impose consequences, and those consequences are far harsher than any number can convey. Knowing the distance is one thing, trying to cross it is another, and it is in the trying that the invisible gulf between solar systems stops being an abstract number and starts becoming a physical wall that breaks every tool, every plan, and every timeline humanity has ever devised for reaching another world. Start with what we have actually done. The fastest object humanity has ever launched on a trajectory away from the Sun is Voyager 1, travelling at approximately 38,000 miles per hour. We covered this just a moment ago. 75,000 years to reach the Alpha Centauri system. That number alone should end the conversation. 75,000 years is roughly 10 times longer than all of recorded human history. No material we have ever manufactured would survive that journey intact. No power source we have ever built would last a fraction of that time. No communication system we have ever designed could maintain contact across decades, let alone millennia. Voyager 1 is already approaching the limits of its power supply. Its radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity, are fading. Within the next few years, the last instruments will go silent. The spacecraft will continue drifting, but it will be dead. A cold metal husk tumbling through interstellar vacuum with no way to report what it encounters. And it will not even reach the inner edge of the Oort Cloud for another 3 centuries. But Voyager 1 was never designed for interstellar travel. It was designed to visit Jupiter and Saturn. Its current trajectory is a happy accident of mission planning, not a deliberate attempt to cross the void. Surely, people argue, we could do better if we actually tried. Surely a spacecraft designed specifically for interstellar travel could move faster. The answer is yes, in theory. But the improvements are far smaller than most people assume, and the remaining distances are far larger than any improvement can overcome within a human lifetime. Consider speed. The Parker Solar Probe, launched in 2018, is currently the fastest human-made object relative to the Sun, reaching speeds above 430,000 miles per hour during its closest solar approaches. That is more than 11 times faster than Voyager 1. At that velocity, the trip to Alpha Centauri would take roughly 6,700 years, a massive improvement over 75,000, and still utterly impossible for any crewed mission, any retrievable probe, or any technology that requires maintenance, repair, or communication with Earth. What about more advanced propulsion? Engineers have proposed concepts that could theoretically achieve much higher velocities. Ion drives, nuclear pulse propulsion, fusion rockets, antimatter engines. Each one exists at a different point on the spectrum, between demonstrated technology and pure speculation. Ion drives are real and operational, but produce tiny accelerations over long periods, reaching speeds that are faster than chemical rockets but still far too slow for interstellar distances. Nuclear pulse propulsion, the idea of detonating nuclear bombs behind a spacecraft to push it forward, was studied seriously in the 1950s and 60s under a program called Project Orion, but was never built due to the obvious complications of launching nuclear weapons into space. Fusion propulsion remains theoretical. No one has built a fusion engine that produces net energy, let alone one that could accelerate a spacecraft. Antimatter propulsion is even further out. Producing antimatter in useful quantities requires more energy than any civilization on Earth currently generates, and storing it without annihilation is an unsolved problem. But suppose, generously, that humanity solves one of these problems. Suppose we build a spacecraft capable of reaching 1% of the speed of light. That is approximately 6.7 million miles per hour, 176 times faster than Voyager 1. At 1% of light speed, the journey to Alpha Centauri would take roughly 437 years. Better. But still, a journey that spans more than 20 human generations. No single person who boards that spacecraft will live to see the destination. Their children will not see it. Their grandchildren will not see it. The people who finally arrive will be the distant descendants of the people who left, separated from the original crew by centuries of life, death, and cultural drift, inside a sealed vessel. Push the speed higher, 10% of the speed of light, 67 million miles per hour. At that velocity, the trip to the nearest star system takes about 43 years. Now we are approaching something that a single human lifespan could theoretically contain. A person who left Earth at age 25 might arrive at 68, battered, aged, and incomprehensibly far from home, but alive. This is the threshold where interstellar travel starts to become conceivable for individual humans, rather than for lineages. But 10% of light speed is a fantasy by current engineering standards. The energy required to accelerate even a modest spacecraft to that velocity is staggering. A 1,000-kilogram probe moving at 10% of light speed carries kinetic energy equivalent to roughly 450 million billion joules. That is comparable to the energy released by several hundred nuclear warheads. Accelerating a crewed vessel with life support, shielding, supplies, and structural mass would require orders of magnitude more energy. No propulsion system that has ever been built or credibly designed comes close to delivering that kind of performance for a payload large enough to carry human beings. The most ambitious interstellar mission concept that received serious funding and attention in recent years was Breakthrough Starshot. Announced in 2016 with $100 million in backing from investor Yuri Milner and support from physicist Stephen Hawking, Starshot proposed an entirely different approach to interstellar travel. Instead of accelerating a large spacecraft, the concept called for sending a swarm of gram-scale probes, each roughly the size of a postage stamp, attached to ultra-thin reflective sails about 4 meters across. A ground-based array of lasers would fire a concentrated beam at each sail, accelerating the tiny probe to approximately 20% of the speed of light within minutes. At that speed, the probe would reach the Alpha Centauri system in roughly 20 years. Upon arrival, it would fly through the system at tremendous velocity, capturing images and data during a brief flyby, then beam the information back to Earth using a tiny onboard laser. The return signal, traveling at light speed, would take an additional 4+ years to arrive. Total mission time from launch to data received on Earth, approximately 24 to 25 years. It was the most credible interstellar mission proposal ever seriously funded, and by 2025, it was on indefinite hold. A Scientific American investigation revealed that of the $100 million pledged, only approximately $4.5 million had actually been spent, distributed across roughly 30 research contracts. The engineering challenges proved immense. The laser array would need to deliver approximately 100 gigawatts of power, focused on a sail smaller than a car, for several minutes, without vaporizing the sail or destabilizing its trajectory. The sail material needed to reflect more than 99% of incident light at the specific laser wavelength to survive the acceleration. The probe itself needed to carry a camera, a communication laser, a power source, navigation sensors, and a computer, all within a mass of roughly 1 gram. Each of these requirements pushed against the boundaries of what materials science, optics, and microelectronics could deliver. Progress was made on individual components. Researchers at several universities developed promising sail materials and demonstrated that AI-designed photonic crystal structures could dramatically reduce manufacturing costs. A test CubeSat was deployed from the International Space Station in late 2025, validating certain holographic and sail deployment technologies. But the integrated system, the full laser array, the complete nanocraft, the targeting and tracking infrastructure remained far from realization. And even if Starshot had succeeded, it would not have carried a human being. It would not have carried a message that could be read by anyone at the destination. It would have sent a chip-sized camera on a flyby so fast that the entire encounter with the Alpha Centauri system would last only a few hours, at a velocity so high that course corrections would be nearly impossible. This was the best-case scenario, a postage stamp screaming through another solar system at 37,000 miles per second, snapping photographs, then vanishing into the dark on the other side. Never to slow down, never to orbit, never to land. That is what 20% of light speed buys you. A glimpse, not a visit. But the failure of even our most ambitious concepts to offer more than a glimpse reveals something deeper about the void. The problem is not just that we lack the speed to cross it quickly, it is that the crossing itself, even if achieved, would be an experience so alien to human existence that no traveller would emerge from it unchanged, if they emerged at all. Imagine you are aboard a vessel travelling at 10% of light speed toward the Alpha Centauri system. The acceleration phase is over. You have reached cruise velocity. The engines are silent. Outside your hull, the universe has not changed in any way you can perceive. There is no wind. There is no scenery passing by. There are no landmarks approaching or receding. The stars ahead look exactly as they did when you left Earth, because even at 67 million miles per hour, you are moving so slowly relative to the distances involved that the constellation patterns will not visibly shift for years. Look out the forward window and you see the same sky. Look out the rear window and you see the same sky. Nothing changes. Nothing happens. The void does not offer you any confirmation that you are moving at all. The temperature outside the hull hovers a few degrees above absolute zero. The interstellar medium is so sparse that individual hydrogen atoms, separated by distances of roughly a centimetre, drift past with no detectable impact on the ship. There is no sound. Sound requires a medium to travel through, and the space between solar systems contains a medium so thin that it is functionally indistinguishable from perfect vacuum. If the ship's engines are off and its machinery is silent, the exterior environment is the most complete silence that nature can produce. Not the quiet of a rural night, not the hush of an empty room, an absence so total that the concept of sound ceases to apply. The radiation environment is relentless. Galactic cosmic rays, high-energy particles born from supernovae and other violent events across the galaxy, stream through the void in every direction at nearly the speed of light. These particles do not stop for shielding unless the shielding is exceptionally thick. They penetrate metal, they penetrate flesh, they penetrate DNA. On Earth, the planet's magnetic field and atmosphere deflect or absorb the vast majority of cosmic radiation before it reaches the surface. Inside the solar system, the Sun's magnetic field provides an additional layer of protection called the heliosphere, but between solar systems, both shields are absent. A vessel in interstellar space is exposed to the full intensity of galactic cosmic radiation with no natural protection whatsoever. Every day of the crossing, every crew member absorbs radiation. The cumulative dose over a 43-year transit would significantly exceed the lifetime dose limits that NASA currently imposes on astronauts. Even with substantial shielding, the biological consequences, elevated cancer risk, potential neurological damage, possible effects on fertility and genetic integrity, would accumulate silently, invisibly, for the entire duration of the voyage. And through all of this, the view does not change. For years, the human mind requires novelty, stimulus, the sense that time is producing change. The void between solar systems offers none. A crew member who looks out the window on day 1 of the crossing and looks out the window on day 3650, 10 years later, sees the same stars in the same positions. The destination star has grown marginally brighter. The home star has grown marginally dimmer. That is the total visible change after a decade of travel. The psychological weight of this sameness is difficult to overstate. Submariners who serve 6-month deployments underwater report significant mental strain from the monotony of an unchanging environment. Antarctic researchers who winter over in darkness for months describe depression, cognitive decline, and interpersonal conflict triggered by the sameness of their surroundings. An interstellar transit would impose that same monotony for decades, with no shore leave, no resupply, no visitors, no new faces, no horizon, and no way out. The void is not merely empty. It is aggressively, overwhelmingly, psychologically empty. It offers nothing to the senses and demands everything from the mind. Now, set aside travel entirely. Suppose you do not need to send a spacecraft. Suppose you only need to send a message. Surely communication across the void should be simpler. Light moves at the maximum speed the universe allows. A radio signal or laser pulse aimed at the Alpha Centauri system departs Earth and arrives approximately 4.37 years later. No fuel required. No spacecraft to build. Just photons crossing vacuum at the fastest possible rate. 4.37 years. That is how long it takes for a single sentence to reach the nearest star system, and 4.37 more years for the reply to return. A minimum round-trip communication time of roughly 8.74 years. Send a question today, receive an answer in 2035 at the earliest. That is not a conversation. That is not even a correspondence. It is a message in a bottle tossed into an ocean where the currents take nearly a decade to complete one cycle. And that is the best case, the nearest system, the shortest possible delay. For Barnard's star, the round trip is approximately 12 years. For Wolf 359, nearly 16 years. For Sirius, over 17 years. For Tau Ceti, roughly 24 years. For Epsilon Eridani, about 21 years. Every light year of additional distance adds 2 more years to the simplest possible exchange. Within just the nearest handful of star systems, communication delays stretch from a decade to a quarter century. Think about what this means in practical terms. Imagine you are an astronaut who has somehow reached the Alpha Centauri system. You discover something extraordinary. An ocean beneath the ice of a moon orbiting Proxima b. Signs of biological chemistry in the atmosphere. Something that demands immediate consultation with scientists on Earth. You compose your message, compress the data, aim your transmitter, and fire. The signal leaves at light speed. 4.37 years later, it arrives at Earth. Scientists receive it, analyze the data, debate the findings, formulate a response. They transmit their reply. 4.37 years later, you receive it. Nearly 9 years have passed since you asked the question. Whatever you found, whatever decision needed to be made, you made it alone, years ago, without guidance, because guidance could not arrive in time to matter. This is what the void does to communication. It does not merely slow it down. It renders it functionally useless for anything requiring timely interaction. No real-time conversation is possible. No collaborative decision-making is possible. No negotiation, no emergency consultation, no shared experience of a simultaneous event is possible between two solar systems. Every exchange is a monologue delivered into a void, followed by years of silence, followed by another monologue in response. The people on each end of the exchange are not communicating in any meaningful human sense. They are leaving messages for future versions of each other, versions who will have lived years of unshared experience between each exchange. Now expand this beyond a single exchange and consider what these delays do to every form of sustained human connection across the void. Think about governance. If a human colony existed in the Alpha Centauri system, Earth could not govern it. A directive sent from Earth would arrive 4.37 years after it was issued. The colony's acknowledgement would return 4.37 years after that. Nearly 9 years between an order and confirmation that it was received. By the time Earth learned whether its policy had been implemented, the conditions that prompted the policy would have changed beyond recognition. Laws passed on Earth would be obsolete by the time they arrived at the colony. Political leadership would change between exchanges. The colony would have no choice but to govern itself, making decisions in real time while Earth's input arrived as historical artifacts from a world that no longer existed in the form the colonists last knew. Think about relationships. A parent who stayed on Earth while their child departed for Alpha Centauri would send a message on the child's 30th birthday. The child would receive it at age 34. Their reply would reach the parent when the child was 38, and the parent was 8 years older than when they pressed send. The exchanges would grow thinner over time, not from lack of love, but from the slow erosion of shared context. The parent and child would inhabit different presents, separated by a delay so long that each message arrives in a world the sender cannot imagine. Births, deaths, illnesses, triumphs, every milestone in a human life would reach the other side years after it happened. You would learn that your grandchild was born 4 years after the birth. You would learn that your parent had died 4 years after the funeral. Grief and joy would arrive in the wrong season, out of sync with the emotions of the people who sent them. The void does not just slow down love, it dislocates it in time, turning every emotional exchange into an artifact from a past that has already moved on. Think about science. A collaborative research project between Earth and a colony at Alpha Centauri would operate on a cycle of nearly 9 years per exchange. A hypothesis proposed by Earth scientists would arrive at the colony 4 years later. The colony's experimental results would return 4 years after that. One iteration of the scientific method, one cycle of propose, test, report, revise would consume nearly a decade. Research that requires dozens of iterations, which is most serious science, would take centuries to complete across the void. The two communities of scientists would inevitably diverge, developing independent research programs, independent methodologies, independent bodies of knowledge that would drift apart over generations until the two civilizations were doing science in fundamentally different ways, unable to effectively collaborate because the communication channel between them operates at a pace slower than institutional memory. Now consider rescue. This is where the distance becomes not just inconvenient but lethal. If a crewed mission to the Alpha Centauri system suffered a catastrophic failure, a hull breach, a power system collapse, a medical emergency beyond the crew's ability to treat, Earth would not learn about it for over 4 years. Even if a rescue mission could be launched the instant the distress signal arrived, and even if that rescue mission travelled at 10% of light speed, which no spacecraft can do, the rescuers would not arrive for another 43 years. Total time from emergency to rescue, nearly half a century. The crew would be dead for decades before help even entered the same star system. In practical terms, there is no rescue between solar systems. There is no resupply. There is no reinforcement. There is no cavalry. Any vessel that enters the void between systems is on its own, from the moment it leaves the gravitational influence of its home star until the moment it enters the gravitational influence of the destination star, and that transit takes years or decades at minimum and millennia at current speeds. During that entire crossing, the vessel is beyond the reach of any assistance from any source. If something breaks, the crew fixes it or they die. If supplies run short, they ration or they die. If a medical condition arises that exceeds their onboard capability, they endure it or they die. The void does not negotiate. It does not offer second chances. It is an environment of absolute self-reliance, enforced by distances that make outside help physically impossible. This is fundamentally different from any form of exploration humans have ever attempted. When European ships crossed the Atlantic in the 15th and 16th centuries, the journey took weeks. Supplies could be rationed for months. Rescue from other ships was unlikely, but not physically impossible. When Apollo astronauts traveled to the Moon, the round trip took days. Communication with Earth was nearly instantaneous. Abort options existed at every stage of the mission. Even Mars, the most distant destination seriously discussed for crewed exploration, sits at most about 22 light minutes away. A distress signal reaches Earth in under half an hour. a response returns just as quickly. Resupply missions could arrive in months. Mars is dangerous, but it is reachable, supportable, and connected to Earth by communication delays measured in minutes rather than years. The void between solar systems obliterates all of that. It takes the model of exploration that humans have refined over centuries, a model based on communication, resupply, and rescue, and it discards every component. What remains is not exploration in any sense that history recognizes. It is exile with a destination. This brings us to the generation ship, the concept most frequently invoked when people try to imagine crude interstellar travel using plausible technology. The idea is straightforward in principle. If no propulsion system can carry humans to another star within a single lifetime, build a vessel large enough and self-sufficient enough to sustain a human population across multiple generations. The people who leave Earth will not arrive. Their descendants will. The ship becomes a world unto itself, a sealed habitat carrying everything needed for human survival across centuries or millennia of transit through the void. The engineering challenges are almost beyond enumeration. Start with radiation. Outside the protective magnetic field of a star, interstellar space is saturated with galactic cosmic rays, high-energy particles that penetrate conventional shielding and damage biological tissue at the cellular level. Long-term exposure increases cancer risk, degrades the central nervous system, and causes cumulative damage to DNA. Shielding a generation ship against cosmic radiation for centuries requires either enormous mass, which makes the ship harder to accelerate and decelerate, or active magnetic shielding systems that have never been built at the required scale and must operate without failure for longer than any machine in human history has ever functioned. Then consider the biosphere. A generation ship must carry or grow all of its food, recycle all of its water, regenerate all of its oxygen, and process all of its waste in a perfectly closed loop for the entire duration of the journey. No resupply is possible. Every calorie consumed must be produced on board. Every molecule of breathable air must be recycled from exhaled carbon dioxide. The International Space Station, the most complex closed environment habitat ever built, relies on regular resupply missions from Earth and still cannot fully close its water or oxygen loops. Scaling that system to support hundreds or thousands of people for centuries with zero external input represents an engineering challenge that is not merely unsolved but barely even scoped. Genetics poses another problem. A viable breeding population requires sufficient genetic diversity to avoid the accumulated damage of inbreeding over many generations. Estimates vary, but most population genetics models suggest a minimum founding population of several hundred to several thousand individuals to maintain healthy genetic diversity across the centuries or millennia of an interstellar crossing. That means the ship must sustain not a small crew but a small civilization, complete with social structures, governance, education, conflict resolution, and cultural continuity across generations that will be born, live, and die without ever seeing a sky, a horizon, or a world outside the hull. The sociological challenges may be the most daunting of all. How do you maintain a functioning society inside a sealed vessel for 500 years? 1,000 years? How do you prevent factionalism, rebellion, resource hoarding, or despair across generations that had no choice in their confinement? The people who board the ship choose to go. Their children do not, their grandchildren do not. 15 generations into the journey, the inhabitants of the ship are not explorers. They are prisoners of a decision made by ancestors they never knew, serving a sentence measured in lifetimes for a destination they have never seen and may not even believe is real. No human society has ever maintained cultural continuity, political stability, and shared purpose for the duration a generation ship would require. The longest-lasting civilizations in human history endured for a few thousand years at most, and they had continents to spread across, climates to adapt to, and neighbors to trade with. A generation ship has none of that. It has walls. But beyond even the social and biological challenges lies a problem that is rarely confronted directly: the mechanical reality of maintaining a complex machine for centuries or millennia with no external support. Every engineered system degrades, every material fatigues, every component has a lifespan, and that lifespan is almost always shorter than the duration of an interstellar crossing. Consider the simplest example, a water recycling pump. On Earth, such a pump might last 10 years before requiring replacement. On the International Space Station, redundant systems and regular resupply from Earth ensure that a failing pump can be swapped. On a generation ship 800 years into a 1,000-year crossing, the situation is entirely different. The original pump failed centuries ago. Its first replacement failed after that. Somewhere around generation 12, the crew replaced it with a version they manufactured from onboard materials. That version used a slightly different alloy because the original alloy required a mineral that had been fully consumed 200 years prior. The replacement alloy is weaker. It corrodes faster. The pump now needs servicing every 3 years instead of every 10. The knowledge of how the original pump was designed has degraded over time, because the engineering manuals stored digitally depend on a file format that the ship's current computing systems can barely read, since those systems themselves have been rebuilt multiple times from scavenged components. This is the cascading failure problem, and it applies to every system on the ship. Air recyclers, water purifiers, structural seals, electrical conduits, radiation shielding. Each system depends on other systems for maintenance, and each system degrades independently on its own timeline. A hull micrometeorite seal that was designed to last 50 years must instead last 1,000, or be replaced and re-replaced dozens of times by people who did not design it, using materials that were not specified for it, following procedures that have been rewritten and simplified and partially forgotten across centuries of oral and digital transmission. The ship is not a static structure. It is a living machine that must be continuously rebuilt from the inside by its own inhabitants, using only the finite resources it carries, for longer than any machine has ever operated in human history. No terrestrial analogy captures this challenge, because every machine on Earth exists within an industrial civilization that can supply replacement parts, raw materials, and expert knowledge from outside. A generation ship has no outside. It is the only factory, the only mine, the only university, the only hospital, the only library that its inhabitants will ever know. When something breaks that nobody aboard knows how to fix, it stays broken. When a critical resource runs out that cannot be synthesized from remaining materials, it stays gone. The margin for error is zero, and the timeline for maintaining that zero margin extends across centuries that would humble any engineering project ever attempted on Earth. Every one of these problems, radiation, biosphere, genetics, sociology, and now mechanical endurance, is individually unsolved. Combined, they form a barrier so formidable that no serious engineering proposal for a generation ship has ever advanced beyond the conceptual stage. The generation ship is not a plan, it is a thought experiment. It is what you arrive at when you accept that the void between solar systems cannot be crossed quickly, and you ask what it would take to cross it slowly. The answer is, more than any technology, any society, and any human institution has ever demonstrated the ability to deliver. The void does not just resist speed, it resists patience. It resists endurance. It resists every strategy humans have imagined for overcoming it, whether fast or slow, crude or uncrude, physical or communicative. And this is still only the nearest system. Every challenge described here applies to a crossing of 4.37 light-years. Double the distance to Barnard's star and the transit time doubles, the radiation exposure doubles, the biosphere duration doubles, the sociological strain doubles. Triple it for systems at 12 or 15 light-years. The generation ship that cannot be built for a 4 light-year crossing becomes even more impossible for an 8 light-year crossing, and unthinkable for a 20 light-year crossing. The void scales its punishment with distance, and the distances escalate rapidly once you move past the single nearest neighbour. The invisible distance between solar systems does not merely make travel difficult, it makes travel, communication, rescue, and sustained connection between star systems functionally impossible using any technology that currently exists, or is credibly projected within the foreseeable future. The void is not an engineering problem awaiting a clever solution. It is a physical condition imposed by the geometry of the local universe, enforced by the speed of light, and deepened by the sheer scale of the emptiness between gravitational territories that are themselves enormous. Every comfortable idea about interstellar civilization, about networks of connected star systems, about neighbors communicating across the light years, about rescue ships arriving from a nearby system, about trade routes and alliances and shared knowledge, all of it dissolves when you confront what the void actually does to every form of connection humans have ever relied on. The void does not connect star systems, it severs them. It enforces isolation so total that each system, with all its worlds and all its potential for life, exists as a self-contained reality with no meaningful link to any other. But the deepest shock is not what the void does to our technology. It is what the void reveals about the structure of the universe we live in. The emptiness between solar systems is not a problem. It is the architecture. It is not the exception to how the local cosmos is organized. It is the rule. And once you understand that, once you stop seeing the void as an obstacle and start seeing it as the dominant feature of the local universe, the meaning of the night sky changes permanently. You have now seen the numbers. You have seen how large each solar system is, how far apart they sit, and what the void between them does to every human attempt at travel, communication, and connection. But numbers, even staggering ones, can be absorbed and filed away. The brain processes them, assigns them to the category of very large, and returns to its default assumptions. The night sky still looks the same. The stars still seem close. The word neighbor still feels warm. What the numbers alone cannot do is change the way you see the local universe. For that, you need to understand not just the size of the emptiness, but its role. The void between solar systems is not a gap in the structure of the local cosmos. It is the structure. And once you see that, the meaning of the night sky inverts completely. Start with a simple exercise. Picture the volume of space within 20 light-years of the Sun. This is the local stellar neighborhood, the region astronomers refer to when they discuss nearby star systems. It contains roughly 100 known stars, organized into perhaps 70 or 80 distinct systems. Some are singles like Barnard's star. Some are binaries like Sirius A and B. Some are triples like Alpha Centauri. Together, they represent the closest collection of stellar neighbors our solar system has. 20 light-years in every direction. That is the neighborhood. Now calculate the volume. A sphere with a radius of 20 light-years contains approximately 33,500 cubic light-years of space. 100 stars in 33,500 cubic light-years. That means, on average, each star occupies a private volume of roughly 335 cubic light-years. Each system floats at the center of its own vast empty territory, separated from every other system by light-years of vacuum. The stars are not clustered, they are not grouped, they are not arranged in any pattern that suggests proximity or connection. They are scattered, randomly and thinly, across a volume of space so large that the systems themselves are almost negligible compared to the emptiness between them. How negligible? Consider the fraction of that volume that actually contains anything. Each solar system, measured generously to include the full extent of its Oort cloud, occupies a sphere, perhaps 1.6 light-years in radius. The volume of that sphere is approximately 17 cubic light-years. 17 cubic light-years of gravitational territory per system, out of 335 cubic light-years of allocated space. That means each system fills roughly 5% of its share of the local volume. The remaining 95% is void. Not the tenuous, debris-scattered void of the Oort cloud, but genuine interstellar vacuum, space where no star's gravity dominates, where no frozen body drifts, where nothing exists except stray hydrogen atoms and the faint wash of starlight from every direction. And even that 5% is misleading, because the Oort cloud itself is almost entirely empty. The objects within it are separated by millions of miles. The density of matter in the Oort cloud is so low that it is functionally indistinguishable from the interstellar medium beyond it. If you count only the regions where matter is dense enough to form structures, where planets orbit, where moons hold oceans, where atmospheres trap heat, the fraction of local space that contains anything meaningful drops to a number so small it rounds to zero. The local universe is not a network of star systems with space between them. It is a vast, almost featureless emptiness, with star systems embedded in it, like specks of dust suspended in a cathedral. The emptiness is the cathedral, the dust is incidental, the void is not the background. The void is the foreground, the middle ground, and the substance of the local cosmos. Stars are the interruptions. This inversion of perspective is the key to understanding why the invisible distance between solar systems is worse than people think. Human beings instinctively organize their mental picture of the cosmos around the bright objects. Stars, planets, galaxies. These are the things we see, the things we name, the things we tell stories about. The emptiness between them has no name, no story, and no presence in our visual field. It is invisible by definition. You cannot see the absence of light. You cannot photograph a void. The night sky shows you only what glows and hides everything that does not. This creates a cognitive map where the universe appears to be made of objects, with emptiness serving as a neutral, featureless backdrop, like the white space on a printed page. But the white space is the page. The text is the exception. The local universe is overwhelmingly, crushingly, definitionally empty. The stars are rare, the planetary systems are rarer, the worlds that might harbour life are rarest of all. And the spaces between all of these things are so large, so featureless, and so absolute that they define the character of the cosmos far more than the objects they separate. When you look at the night sky and see Alpha Centauri, you are seeing a lighthouse. It is a brilliant point of light signalling its existence across the darkness, and like a lighthouse, it tells you that something is there, but it does not tell you how to get there. It does not tell you what lies between you and it. It does not tell you that the water between your shore and that light is deeper, wider, and more featureless than any ocean Earth has ever held. The light creates an illusion of proximity. It creates the feeling that the lighthouse is part of your world, that it belongs to the same continuous environment, that you could reach it if you had the right vessel. But the ocean between you and that lighthouse is not water, it is vacuum, and it is not miles wide. It is trillions of miles wide, and there is no vessel. This is what invisible means in the title of this story. The distance between solar systems is invisible not because it is hidden by some mysterious force, but because the human eye and the human brain cannot perceive it. You see the stars. You do not see the space between them. You register the points of light and unconsciously assume that the dark patches between those points are small, manageable, navigable. They are none of those things. The dark patches are the dominant reality. They are the defining feature of the local cosmos. And they are invisible to you every single night, hidden in plain sight behind the beauty of starlight. Now consider what this means for the idea of a local cosmic neighbourhood. Astronomers use that phrase casually. The local neighbourhood, the nearby stars, the stellar vicinity. These terms suggest a community, a collection of systems that share some meaningful connection by virtue of their relative proximity. And in a purely gravitational sense, the systems within 20 light-years of the Sun do share a region of the galaxy. They move through space in roughly similar directions. They experience roughly similar galactic tidal forces. They belong to the same sparse arm of the same spiral galaxy. But proximity and connection are not the same thing. The systems in our local volume approximate only in the astronomical sense that they are closer to us than other systems farther out. They are not connected by any physical medium that would allow interaction. No bridge of matter links them. No current of energy flows between them. No signal passes between them unless deliberately sent, and even then, the signal takes years to arrive and carries no possibility of reply within a human attention span. The systems are near each other on a galactic map, and utterly isolated from each other in every practical sense. This is the difference between a neighbourhood and an archipelago. A neighbourhood is a collection of homes connected by streets, by shared infrastructure, by the ability to walk next door and borrow a cup of sugar. An archipelago is a collection of islands separated by open water, where each island sustains itself independently, and contact between islands requires a deliberate, difficult, and dangerous crossing. The local stellar environment is not a neighbourhood. It is an archipelago, and the ocean between the islands is not water but vacuum, and it is not miles wide but light years wide. and no ship that has ever been built or credibly designed can cross it in less than a human lifetime. The word exile may sound dramatic, but it is precise. To be exiled is to be cut off from others by a distance or barrier that prevents return or contact. Every solar system in the local volume exists in a state of exile from every other solar system, not because anyone imposed it, not because some cosmic authority decreed it, but because the geometry of the universe, the spacing of stars, the speed of light, and the energy requirements of travel combine to create a condition of isolation so thorough that it functions exactly like exile. Each system is whole. Each system may contain worlds, oceans, atmospheres, perhaps even life, and each system is cut off from every other by a gulf that no technology we possess or can foresee can meaningfully bridge. Consider Proxima b, an Earth-sized world in the habitable zone of the nearest star. If that planet holds liquid water, if it has an atmosphere, if some form of biology has taken root there, then life exists 4.24 light-years from Earth. The most profound discovery in the history of science would be confirmed. We are not alone, and we would be unable to visit, unable to communicate in real time, unable to send aid or receive it, unable to share knowledge within any time frame that a single human life could encompass. We would know that another living world exists. We would be able to point to it in the sky, and we would be separated from it by a void so absolute that the knowledge itself becomes a kind of torment. Proof of companionship enforced by proof of isolation. The universe saying, "Here, look, you are not alone and in the same breath, but you will never touch." And now consider what happens if Proxima b is not the only one. Consider the possibility that biology is not rare but common. Barnard's star has 4 confirmed planets. Alpha Centauri A may have a gas giant and could harbour additional rocky worlds. Tau Ceti, roughly 12 light-years away, has candidate planets in its habitable zone. Epsilon Eridani, about 10.5 light-years away, hosts a confirmed Jupiter-sized world and may have smaller companions not yet detected. Ross 128, roughly 11 light-years away, has a confirmed Earth-sized planet near its habitable zone. Within just the nearest 20 light-years, the number of worlds that could theoretically support some form of biology may reach into the dozens, perhaps more, as detection methods improve and smaller planets become visible. Now suppose, for the sake of the thought experiment, that life has indeed taken hold on 5 of those worlds, or 10, or 20. Suppose that biology is scattered across the local volume, the way the stars themselves are scattered, thinly but persistently. One living world here, another there, another far off in a different direction. What does that change about the isolation? Nothing. 10 living worlds within 20 light-years of Earth would not form a community. They would form 10 separate instances of the same solitude. Each living world would sit at the center of its own vast pocket of void, separated from every other living world by distances measured in light-years, connected to none of them by anything faster than the crawl of light itself. Each world would evolve its biology independently. Each would develop its own chemistry, its own ecosystems, its own solutions to the problem of survival, without any input from, awareness of, or influence on any of the others. They would not share genetic material. They would not trade resources. They would not learn from each other's experiments. They would not even know each other existed unless one of them developed the technology to detect the faint atmospheric signatures of life on a world orbiting a distant star. And even then, the detection would arrive as information only, unreachable, untouchable, a portrait of a stranger seen through a window that does not open. The archipelago does not become less harsh when more islands appear. It becomes more cruel, because the density of unreachable companionship increases while the distance between each pair of islands remains unchanged. Every new living world discovered in the local volume is another proof of what biology can achieve, and another proof of what the void prevents. The more common life turns out to be, the more isolated each instance of it becomes in any meaningful sense, because the number of companions you can see but never visit, can detect but never contact within a lifetime, grows with every discovery, and every one of those companions sits behind the same impassable wall of vacuum and time. This is perhaps the cruelest feature of the void between solar systems. It does not prevent life from arising. It allows life to arise, perhaps frequently, perhaps abundantly, scattered across the galaxy on millions or billions of worlds. And then it separates each instance of life from every other instance with distances so extreme that the word separation does not capture the reality. The void is not hostile to life, it is indifferent to life. It lets life bloom wherever conditions permit, and then it ensures that each bloom exists alone, sealed inside its own solar system, surrounded by light years of silence, permanently unaware of the blooms on the other side unless it develops the instruments to see them, and the wisdom to understand that seeing is not the same as reaching. This is not a failure of human ambition. It is not a temporary limitation that cleverer engineering will eventually overcome. It is a structural feature of the cosmos. The distances between solar systems are not accidents of stellar formation that happen to place things far apart. They are the natural consequence of how stars form, how gravity distributes matter, and how the galaxy organizes itself on large scales. And to understand why the void is this large, you need to know that it was not always so. The sun was not born in isolation. It was born in a crowd. Approximately 4.6 billion years ago, in a region of the Milky Way dense with gas and dust, a massive molecular cloud began to collapse under its own gravity. As it collapsed, it fragmented into hundreds or thousands of smaller cores, each one contracting independently, each one heating up as gravitational energy converted to thermal energy, each one eventually igniting nuclear fusion and becoming a star. The sun was one of those stars. It was born alongside siblings, perhaps 2,000 of them, perhaps more, packed into a cluster where the distances between neighboring newborn systems were measured not in light years but in fractions of a light year. For a brief window of cosmic time, the sun had genuine neighbors, not in the weakened astronomical sense of the word, where neighbor means the nearest point of light across a void of trillions of miles. In the real sense, systems close enough that their gravitational territories overlapped, systems close enough that material ejected from one could plausibly drift into another within thousands of years rather than millions. Systems close enough that, had any form of life existed in those early days, the distances between worlds would have been a challenge rather than an impossibility. But that window closed. Molecular clouds do not hold their children. The same gravitational dynamics that formed the cluster also began to dissolve it. The young stars, each one carrying its own velocity, inherited from the turbulence of the collapsing cloud, drifted apart. Some were flung outward by close gravitational encounters with siblings. Others were gradually stripped away by the tidal forces of the galaxy itself, which gently but persistently pulled the cluster apart as it orbited the galactic center. Over hundreds of millions of years, the tight birthplace dispersed. Stars that had been light months apart became light years apart. Stars that had been light years apart became tens of light years apart. The siblings scattered across the Orion Arm, then across the wider disk of the galaxy, each one following its own unique orbital path around the galactic center, at its own unique velocity, each one drifting farther from every other with every passing million years. Today, 4.6 billion years later, the sun's birth siblings are unrecognizable. They are scattered across thousands of light years, mixed into the general population of stars in the galactic disk, chemically similar to the sun, but indistinguishable from unrelated stars with similar compositions. Astronomers have searched for the sun's siblings using chemical fingerprinting, looking for stars with the exact elemental abundances that would mark them as products of the same molecular cloud. A few candidates have been identified, but they sit dozens or hundreds of light years away, so thoroughly dispersed that reconstructing the original cluster is effectively impossible. The family the sun was born into has been dismantled by time and gravity and scattered to the winds of the galaxy. The sparse, isolated local volume we see today is not the original condition of the sun's environment, it is the aftermath. The void between solar systems is not a static feature that has always existed. It is the end product of a slow, irreversible dispersal that took billions of years to complete. The sun once had neighbors in the honest, physical, reachable sense of the word, and it lost every single one of them. Not to catastrophe, not to violence, simply to time and distance and the gentle, patient, unstoppable mechanics of galactic orbits gradually carrying every sibling star away from every other, until the distances between them grew so large that no record of their shared origin could survive except in the chemistry of their cores. The local neighborhood we inhabit now is not a family. It is a collection of strangers. The stars within 20 light-years of the Sun share no common origin. They were born in different molecular clouds, at different times, in different regions of the galaxy. They arrived in this neighborhood through the random shuffling of galactic orbits, each one drifting into the local volume from a different direction, each one passing through on its own trajectory. The Sun is surrounded not by relatives but by passers-by, and the distances between them are the distances that random galactic scattering imposes on unrelated objects sharing the same sparse arm of a spiral galaxy. There is no deeper structure. There is no hidden connection. The apparent neighborhood is an accident of galactic dynamics, and the void between its members is not a gap in something that should be whole. It is the natural, permanent, default condition of interstellar space. The architecture of emptiness extends outward from the local volume without improving. Step beyond 20 light-years and the pattern continues. More systems, more gaps, more void. At 50 light-years, the count of known stars reaches into the thousands, but the volume of space grows as the cube of the radius, meaning the density of systems does not increase. The scattering remains thin. At 100 light-years, the count reaches tens of thousands of stars, but the average spacing between neighbors remains multiple light-years. The galaxy does not become more connected as you zoom out. It remains a vast scattering of isolated gravitational territories at every scale, from the local volume to the spiral arms to the galactic disk as a whole. And this is the Milky Way, a galaxy containing roughly 400 billion stars, 400 billion points of light, and the space between them is so dominant that if you removed every star, every planet, every grain of dust, and left only the vacuum, you would remove less than a trillionth of the galaxy's volume. The galaxy is made of emptiness. The stars are seasoning. Return now to the night sky. You are standing outside. The stars are overhead. They look beautiful. They look close. They look like they belong to a single, shared, connected cosmos. You know now that they do not. Each one of those lights is the center of an enormous gravitational territory. Each territory is separated from every other territory by trillions of miles of vacuum that contains almost nothing. The light from those stars has been traveling for years, decades, centuries to reach your eyes. The stars you see are not where they appear to be. They are not as close as they look. They are not reachable by any means you possess. They are lighthouses on distant shores, and the water between you and every single one of them is deeper and wider than the human mind was built to comprehend. The night sky is a theatre curtain. It is beautiful. It is vast. It is covered in lights that draw your attention and fill you with wonder. But behind that curtain, the stage is empty. The dominant reality of the local cosmos is not stars. It is the absence of stars. It is the trillions of cubic light-years of vacuum that separate every glowing point from every other glowing point. The curtain shows you the decorations and hides the emptiness. And the emptiness is what defines where you live. You live in a solar system. That system is your world. It contains your sun, your planet, your moon, the other planets, the moons of those planets, the asteroids, the comets, the Kuiper belt, and the vast shell of the Oort Cloud extending more than a light-year in every direction. Everything you have ever seen, everything every human has ever touched, everything every spacecraft has ever visited, exists within this single system. It is enormous. It is rich. It is full of complexity and beauty and scientific mystery, and it is an island. Surrounding that island, in every direction, is a void so large that crossing it would outlast civilizations. On the far side of that void, other islands exist. Some of them may harbour worlds with oceans. Some may harbour life. Some may harbour minds that look up at their own night skies and wonder, as you are wondering now, whether anyone else is out there. And every one of those minds, on every one of those worlds, on every one of those islands, is separated from every other by the same invisible, impassable, lightless gulf that separates you from them. The local universe is not a cluster of destinations. It is a scattered archipelago of exile. Each island is complete, each island is alive, and each island is alone. The invisible distance between solar systems is worse than people think, not because the number of miles is large, although it is, not because the travel time is long, although it is, not because communication is slow, although it is. It is worse because the emptiness between systems is not a problem to be solved. It is the way the universe is built. The void is not an obstacle on the road between here and there. The void is the road, and the road has no end, no landmarks, no rest stops, and no one waiting on the other side who knows you are coming. Every comfortable story humanity tells itself about the cosmos, that we live in a neighborhood of stars, that the nearest systems are almost within reach, that the universe is a connected web of worlds waiting to be explored. Every one of those stories is a product of the lie the night sky tells. The sky shows you the lights, it hides the dark, and the dark is where the truth lives. The truth is that each solar system is a self-contained world, separated from every other self-contained world by distances so extreme that they mock the meaning of the word near. The truth is that even the closest neighbouring system, the one that sits right there in the constellation Centaurus, visible to the naked eye on a clear southern night, is so far away that reaching it would require more time, more energy, more endurance, and more luck than humanity has ever assembled for any single purpose. The truth is that the local universe is not a place where solar systems sit near each other. It is a place where solar systems sit alone, surrounded by a silence measured in light years, connected only by the thin, ancient, and unbearably slow thread of light itself. That light is beautiful. It is the only evidence we have that other systems exist, but it carries a hidden message that most people never hear. You can see us, the light says, but you cannot reach us. And behind every star, in every direction, stretching outward in every dimension, the void confirms it. The distance between solar systems is not just far, it is final. Not because the laws of physics forbid crossing it in absolute terms, but because the scale of the crossing, the emptiness of the route, and the isolation it imposes are so extreme that they transform the meaning of what it means to exist in this universe. We do not live in a cosmos of connected worlds, we live in a cosmos of separated ones, and the separation is invisible, silent, and worse than anyone standing beneath a sky full of stars would ever guess. That is the invisible distance between solar systems, not a number to be quoted, not a fact to be memorized, a condition, a permanent, structural, architectural condition of the universe that makes every solar system an island, every star a lighthouse with no harbour, and every sky full of lights a beautiful, ancient, ongoing lie about how close the rest of the universe really is.